Welcome back. The continuation of previous lecture. We'll see the quick animation of how the Hall field is working for a better understanding. This is quick review of how the Hall field is working. You can see that if there is no magnetic field influence, the current will be straightforward. But when start applying the magnetic field, electron is going to move upward to the plate based on the direction of magnetic field. If I change the direction of magnetic field, it's going to be opposite. It's something important phenomena. Again, the continuation of this, if I break this two plates and make it to the first and the last, if it is a like negative, this is a positive, so I can influence in this way also. Okay, so the direction is going to change in the voltmeter in the reading. You can see that. So whenever there is a direction, the change in the direction of the magnetic field is something very useful. If we get this the rotation of electrons in the different directions, I can find out it is what kind of charges it is. So basically electrons carries the charges in the metal. So if I change the magnetic field, it is going to change in the opposite direction. So if I go to the semiconductor, the carrier can be holes also. So that time the holes will react in the different direction and electrons will act in the different direction. So I can make out the carriers, whether it is a holes or electrons. It's going to plays a very good role to find out what kind of carrier it is. So it is one of way to find which are the carrier it is, and also what is the magnetic field strength of in the given situations. I can find out what is the magnetic field. So we quickly go back to the main topic. So this is a current carrying conductor influenced by the magnetic field. I will include one of the pictures, good pictures of Hall effect, so we'll get a better understanding of it. So this is a diagram showing this 3D diagram of a conductor. It's same like drawn earlier. So we can see that electrons here, that is a blue color, it's going on the directions of the green, and here the magnetic fields is applied inside to the conductor, as I told earlier. So here the voltage, supply voltage is connected. As you can see, this is the electron current in this direction, and the opposite is conventional current. So we can see this is the conventional current and electron current is flowing in the opposite. So if I take any multimeter and I connect top and bottom of the conductor, if I measure the voltage, this is called Hall voltage. By using Hall field, I can find out what is the Hall voltage. So here the one thing we have to keep it in mind. So what is the direction of the electrons, whether it's go upward or downward? It is basically decided by the magnetic field applied on the conductor. If the magnetic field is going inside the conductor, from it is like inside the screen, so the electrons will go to the top. If the magnetic field is opposite, the electrons will go to the down. So how to determine this? This is basically determined by using right hand rule. That we will see it quickly with the formula. So basically I'll change the background for a better visibility. So here the force acting on charges is called Lorentz force. It's called F. It's equals to the charge times of the velocity of the charge cross product of applied magnetic field. So when the charge velocity is going in this direction, as we mentioned in the previous diagram, and my magnetic field is going inside, that is I can use a symbol like a arrow, because this is we mark this cross mark is we usually tell this is inside the screen. It's like an arrow, it's going inside. If I see the arrow from the behind, we'll get only the cross. So if I put a cross, it's going inside the screen. So if the magnetic field is going inside and v is velocity is going to the left, as a right hand principle, I can write this is my index finger. Always we start with index finger, that is a velocity, and the middle finger is going inside. This is a middle finger, and the B, this is V. So the thumb will be going to the bottom. That is what we call as the resultant of cross product is nothing but the force. That's the Lorentz force. So here the force acting on the electrons in the bottom. So we will get, if we take the angle between these two vector is exactly 90 degree. As you know that dot product, the charge, if I take here, the charge is electron, and if I take the dot cross product, it is V bar into B bar, and here I'll get the sine theta, and I'll get n cap, that is orthogonal vector. So if I take only the scalar component of it, this is actually the magnitude of both sine theta, and n cap is this is a unit vector, which is a orthogonal unit vector. So here, since theta equal to 90 degree, so sine 90 will become 1. So the scalar of the Lorentz force F, E, I just mentioned E of electron Lorentz force, F E is nothing but E into V dot B. Since the electron is negative, I'll put negative here. This is called the Lorentz force acting on the electrons. That is the bottom. Since this electron is a negative, the force is negative. So you have to keep it in mind, should not get confusion here. Since the force is a negative, so it is basically the, if any vector, if I take is the A bar in this direction, so minus A bar will be opposite, or reverse. If the minus A bar in this direction, A bar will be opposite. So the force acting on this conductor, as with this convention V cross B, the force is negative here. Actually the force is the upward direction. So in the previous diagram, I think it is clear why the force is upward, because we are getting a negative force. It's nothing but upward force. So it's nothing but electron is like moving upward due to that force. So whenever electron is there, so electric field will be created. So we know that as a basic relation, the force acting on charges, especially electrons, which is a negative, is nothing but electric field. Okay, so the force I can write as charge times of electric field. So this is equation 2. So it means that, as I already discussed in the previous time, so whenever this electric field I can relate with a gravitation force. So any mass having any particle is having mass, it will it will moved by the gravitation force. So we call as it's nothing but the force, what force we call as mgh. So here is a gravitation force. So here the force acting on electrons we call as an electric field. So here the electric field is negative. Usually the conventions we will write always positive to negative. Electric field always positive to the negative. So here the electric field is nothing but force acting on the charges. So 1 and 2, if I equate it quickly, we'll get V times of P equals to the electric field. So is one of the relations we will get. So here the velocity is nothing but, we know already that two velocity, that is drift velocity, this is the drift velocity plus thermal velocity. that is Vt. This is thermal velocity. Since the thermal velocity is a random, it is not any particular direction, this we can equates to 0. So this can equate to 0. So here the equation, this is 3, can be written as Vd times of B is equals to electric field. And by using a Drutz's classical theory, using a Drutz's theorem, we know that the current density of any conductor, I can write total number of electrons and charge in the electrons and this nothing and drift velocity. This can be also written as drift velocity mobility times of electric field. So from here I can get what is the drift velocity. So drift velocity is nothing but current density and divided by Ne will come here, so minus J divided by Ne. This is drift velocity. I can number this equation as 4. So substitute 4 in third equation. Like it's nothing but in this equation. This is I can write, it's both are similar, so I can write this is 3a. So substitute 4 in 3a. So here I will get minus J over Ne, and magnetic field is nothing but electric field. So from here I can get E is nothing but, here E is nothing but whatever due to the magnetic field, whatever is generated is nothing but the Hall field. Okay, this electric field, just I have to mention here, so whatever the field is generated due to the magnetic field which is measured across the conductor is nothing but Hall field. So it is nothing but minus 1 by Ne times of J into B. So here the 1 divided by Ne I can write as on constant is nothing but now total number of electrons and charge of the electrons. I can write as this is a constant, that is RH. This is called all coefficients. So this is all coefficients. You notice that it is a negative. So any conductor Hall coefficient is negative. So this we can verify with other materials like other than conductor. It may not be always true negative. So we can come to conclusions like it's only the not only the electrons carrying a current. So others like holes also and acceptor donors also can carry the current. So that's why we won't get the negative always. That we will see it. The exception in the case we will see it later. Before we'll find one more relation, something useful for to measure in the practical. So this is can be written as Hall field can be written as RH times of J into B. This I can number as 5. So here what conclusions we will make here is RH always negative, less than 0 for metals, for metals generally, but this is always not true. RH can be also greater than 0, means that not only electrons carry the current. But this is a first proof that you can note down this from the first point. This is the first proof that electrons only traditionally carrying the current. So here I'll write it here, maybe here, electrons only carry the current. Carry the current normally in the conductor. The conductor. So here, but in some cases in semiconductors, not only electrons, and others like holes also can carry the conductor. That conclusion will come to know when we do practical measurement of different conductors, semiconductors, the like alloys. When we do that, we can find out different Hall coefficients. From that we can come to conclusion what carrier is used for a conduction. So for a comparative study, you can see that one of the table is given in the textbook, that I will just give it here. So this is the table you can find in the textbook. This is a different RH value, Hall coefficients value. We can see that sodium, potassium and lithium, alkaline materials will have all negative values, but some metals can have a positive values also. So it's not only electrons going to carry the current, even though this is metals, even holes, this is the electrons. If holes got any electrons, is called positively charged electrons. Okay, so that also can carry the current. So this is exception in the Hall coefficient. Some conductor can have the positive Hall coefficients also. So this is all about the Hall fields, so that we get the important relations with nothing but EH equals to Hall field times of JB, or RH equals to EH divided by J into B. So we will see the problem based on this in the next video. Thank you for listening.